Am I audible? Is the screen visible?
Yes, sir.
Good. Okay. So we talked about the construction of JFET in this last class. This was all done. We just got to know how basically a N-channel JFET and a P-channel JFET is constructed. Okay. We'll continue further with the rest of the discussion as to what is going to happen. Probably, you know, I have already given this explanation in the practical class when we did the simulation, but we'll redo it for the entire class so that everybody understands it. So let me start with the construction part. We will go with the N channel now. So we are trying to understand the operation of N channel JFET. Okay. So what is going to happen in N channel JFET? So if you bring in this JFET, we have a channel which is made up of N. On the either side of it, what you see is a P. In fact, when you do the construction, you write it as P plus because it should be highly concentrated. Okay, so that there is a more effect of gate on the channel. That's the reason why you increase the concentration on the either side of the channel. So one of the terminal we called it as drain. The other terminal becomes the source, and what you have here is the gate. They are internally connected to each other. And this forms a single gate. And if you try to see the JFET available in the laboratory, the physical JFET available, the discrete component available in the laboratory, you will see 4 different terminals in fact. And the 4th terminal is one more gate. So indication that there are 2 gates, but they are internally connected to each other. They are internally connected to each other. Okay. So now as far as the operation is concerned, we should understand what is going to happen when you connect a voltage source to these two. So let us say we apply a positive voltage here. And is there any specific reason as to why we have to apply a positive voltage? Depending on what majority carriers we have got in the channel, this particular supply has to squeeze out all the majority carriers towards it. And majority what we have here is an electron. And that is the reason why we apply a positive voltage here, and we can call it as VDS. And there are cases where the same voltage is also called VDD. So you don't have to worry about it. Okay. And the source is grounded always. The source terminal where the negative is getting connected is always a ground point. So let us for the time being understand what happens when the gate voltage is not present. So this VGS, which is also called as VGG, if that voltage is 0 volts, what will happen? We'll try to understand it. Okay. Remember, there is an electron current which is coming out. So when certain voltage is applied, let us say some minus 10 volts, sorry, plus 10 volts is getting applied here. Electrons will start moving in this direction. So the current is in this direction, and remember that current is because of the electron. But normally when you try to write the current direction in a semiconductor device, we always write the conventional current direction. So it should be like this. It should be getting in, but otherwise electron current is coming out. So the supply will take out all the electrons in the channel, and that forms the electron current, which is ID. But conventional current direction is into the channel, which is the whole current. So the current will come out like this as again ID. So the same ID is flowing everywhere. And this ID, what is indicated here, is because of the hole. Is that clear till here? Now the question is,
Yes, sir.
Yes, sir.
Now what is happening at the gate? As the gate voltage is equal to 0, the significance of these two is not shown there, or P plus is not really affecting the channel here. So when the gate voltage is 0, whatever the current that flows in the channel, let me write that when gate voltage is 0, whatever current that flows in the channel is dash current. What is it? Can you fill in this blank?
Maximum current.
Exactly. It will be the maximum current. And that maximum current is indicated as what? IDS. Yes. IDS stands for current from drain to source, or the current which is flows between drain and source, and this S stands for saturation value. And is this the maximum current that we can get in a JFET? The answer is no. This is not the maximum current which we can get out of a JFET. It all depends on what VDS value you're applying. So for a given VDS value, for a given VDS, you expect certain maximum value which is termed as IDSS. So IDSS is not a fixed value. It depends on what VDS you are feeding to it. Okay, but that will be maximum for gate voltage equal to 0 for a given VDS value. Clear? So that one thing is, I hope, clear to all of you. What happens when gate voltage is not present? Now let us try to apply a gate voltage and see what happens in the transistor. So this is when gate voltage is 0. Let me write that. When, so we can have three cases. When VGS is equal to 0 volts. This is case number 1. What is case number 2? Case number 2 is when VGS is positive. Let us see what happens. Let me take the same diagram to make you guys understand. Thought I can select it. A lot of changes have happened in the whiteboard. This is again an N channel, got two P's on the either side, which are P plus. These two are interconnected together. Source and drain is connected through a supply. Still VDS, which is positive, and now we are going to apply a positive voltage to the gate. This is VGS or VGG. I'm repeating. You can either call it as VGG or VGS. It all depends whether you are very specific to the configuration or you want to generalize the notation. Okay, VGG is a very generic notation. VGS is specific to VGS and VDS are specific to what configuration transistor it is. Can somebody tell me what configuration transistor is this? All these things have been discussed.
Common source.
It's a common source. By default, we take common source. I'm repeating this. I've repeated it many times. Common source is what we normally consider in understanding the operation of a transistor as far as JFET is concerned, and common emitter in BJTs. It's quite common to discuss these two different configurations in both the transistors. So Now we should understand what happens when the VGS value is positive. Can somebody tell me what is really going to happen to the transistor when you apply a positive voltage? Let me exaggerate these two regions. I'm exaggerating these two regions to understand what will happen there. Okay, what is going to happen now? Any good guess? Again, it's all delta. We have discussed about it. When you apply a positive voltage, all the holes which are there in the P will try to move away from the positive supply. Correct? There is a positive connected here. This makes all the holes to move away from the gate terminal. Correct? But at the same time, this VDS what you're applying, normally we consider this VDS to be around, let us say 10 volts, 20 volts like that. This VGS what we apply will be, let us say 1 volt, 2 volt, 3 volts like that. So when you're applying these voltages, and remember these two are P plus. When you're applying this positive voltage to both sides of the gate, all the holes will try to move away. At the same time, you are getting even the positive voltage coming from this side. So all the holes will also be pushed away from the drain. So the source is the one which is going to take in all these holes. So all the holes would move towards the source. That is what we can expect. And all the electrons would try to come towards this positive because you're applying a positive voltage here. But the positive voltage applied to the drain is more compared to the positive voltage applied to the gate. So the number of holes which moves towards this side is again less. The electrons which moves towards this positive is less. The electrons which moves towards this is more. So it means that this is negligible. This is insignificant. This is insignificant. Okay. So the numbers are very less. But the movement of electrons and holes will happen like this. All holes are moving like this. And these holes are coming from the P side. All the electrons which are there in the channel will also try to move towards this apart from moving towards this VDS value. So what I'm trying to tell you is when VGS is positive, when VGS is positive, when VGS is positive, holes in P plus tend to move towards source and electrons in the channel. I'm talking about the majority carriers. So please understand I'm talking about the majority carriers in the individual region, P plus region as well as the N channel region. And electrons in the channel also tend to move towards gate. But the VDS what you're applying is large enough to take away all the electrons towards it, and hence the exchange of carriers what will happen? What I can say is exchange of carriers between gate and channel is very less. So what we can expect is the holes which are coming from the P will also be contributing to the whole current which flows in this direction. I've already given you the indication how ID will flow. ID gets into the drain terminal. This is drain and this is source. ID gets into the drain terminal like this. And that is the whole current. So the holes which are coming from the P place will also be contributing, but the amount is very, very, very less because area wise also the P plus region is very small. And as you're applying a very small VGS value here, the amount of holes which comes out of P plus is also very small. So it's a very insignificant value, and that is why we'll never consider the current which flows in the drain because of the holes which are present in P plus of gate, as it is a very, very small value. Okay, as it is a very, very small value. So till here all okay? Till here everything is fine?
Yes, sir.
Any questions anybody has got? Please mute your mic, Vidya. Okay. So I hope till here all of you are okay. Can I just get a confirmation that you're all following it?
Yes, sir.
Yes,
Raise your
sir.
hand.
Yes,
If you're
sir.
following it, please raise your hand if you're following it. You don't have to unmute, just raise your hand. If I get the majority, I'll proceed further. Good. I've got the majority. That's enough, more than enough for me. Fine. So this is what is going to happen when you're applying a positive voltage. So the conclusion is when positive VGS is applied, current remains at IDSS even though a small raise in the current happens because of poles from P plus region. But that is not considered because it's a very, very small current. That is why we can say that IDSS will always be, it's almost standstill. No changes will happen. No changes is going to happen in the IDSS value, even though theoretically speaking, there has to be a small increase or raise happening in IDSS. Okay, this is as far as VGS is positive is concerned. Let us consider the third case when VGS is negative. What happens when VGS is negative? Let us see. Again, I'll bring the same block, the layer diagram. You have to slightly exaggerate the channel part as well as the gate part, make you understand what will happen in the FET part, channel part. Same positive voltage as far as VDS is concerned. This is N channel. We're having a P plus. There's a P plus even here also. Okay. Now these two are interconnected. This is gate, drain, and source. Source is grounded, and that is why we call it as common source. Gate is now negative, and the other terminal is grounded. So this is as good as source. The source is directly grounded, so that is why you call it as VGS. And you call this as VGS. It's a common source. I'm repeating it so that it fixes in your mind. You will never forget it. Okay. Now I should worry about what is going to happen. Now, let us start with a smaller VGS value. Let us say minus 1 volt getting applied here. VGS is small now. What will happen? It's quite obvious that when the negative voltage is applied, all the holes which were here, let me slightly increase the width of this. So all the holes which are here will try to come towards the negative terminal. It becomes very obvious. Correct? It starts moving towards this. So there is a barrier now getting created. There is a barrier which gets created now. So I can indicate or show a depletion region like this. So slightly the depletion region will increase. Why is it? So because there is a junction or a these two P-N junction is now getting kind of reverse bias, positive voltage being applied, a negative voltage being applied here. So the affinity is more towards this, battery. So hence all the holes will start moving towards it. Most of you or few of you at least may have a question as to why these holes are not moving towards the source side. The reason is very simple. The distance traveled or traversed or the distance that is going to be traversed by these holes to the source side is more compared to this. So most of the holes which try to move towards this may die. That's basically because of the lifetime of the carrier, which is right from this P plus towards the source side. So the lifetime is very less. It will not really go up till this. Instead, it would choose a path which is nearer to it, which is this negative voltage. So that is why all the holes will now start migrating. Earlier, the case was different. You were pushing the holes. That is why they were gaining the velocity. But now things have changed. So negative voltage here will make all the holes to move towards the gate voltage itself. So that makes the barrier to get created. So there is a small raise in the barrier happening. So further increase in the gate voltage will further try to increase the forbidden region or the depletion region. So every time what we are observing is the closing of channel. Earlier, the width was this much. Earlier, the width was this much, the width of the channel. Now the width of the channel has come down to this. Every time there is an increase in the gate voltage, you can see still further channel getting closed. A point reaches where the channel completely get closed. You can see there is absolutely no width left between the two depletions. And that is a point where you say that the current has become equal to 0. And that is what is called as a pinch off point. So when VGS reaches, let me write those points to you. As and when VGS is applied, and remember it is understood it is a negative voltage now because we are discussing this under the title when VGS is negative. As and when VGS is applied and increased, the depletion width increases, and I can say penetrates into the channel. Penetrates into the channel, and that makes the IDS current. From now onwards, instead of calling it as IDS, allow me to call it as just ID, one and the same. ID current makes the ID current to what? ID current to
0.
reduce. Later on, it will become 0, but it will start reducing. So when VGS becomes equal to what is called VP, what is VP? It is called as pinch off voltage. The channel gets completely closed and the ID current becomes equal to 0. This is a point where we say that the transistor has gone to the cutoff point. Earlier it was in saturation, now it is at cutoff. Saturation happens when the gate voltage is 0. Cutoff happens when the gate voltage is pinch off voltage. So now we have kind of, understood the relation that exists between the input voltage and the output current. We've got this relation. So now we have to just put it in the form of a graph, which will be called as a transfer characteristic curve. That is all. Okay. Now we'll try to plot a graph. We'll try to plot a graph, which will be called as. Let's go back just a second. We'll have to plot a graph of ID current versus, I should use VGS versus ID. We should be calling it as VGS versus ID. Graph of VGS versus ID, because VGS sits on x-axis, ID will be on y-axis. Now, what conclusion we draw before I write the graph? Whenever the gate voltage is positive, we hardly see any change happening to the drain current. So I do not have to worry about the positive VGS values. I should only be concentrating on negative VGS value. And we also know when the gate voltage is 0, current is maximum. So with these 3 points, we are ready to plot this graph, which is ID versus VGS. 0. For positive VGS, I don't have to worry about it because the current is anyways would have reached the maximum. It will continue to be maximum with a slight increase in the current. We have to accept that there will be a slight increase in the current, but that is insignificant. So I'll not be bothering about it. But later on, for the negative gate voltages, let me also indicate a point here, which is the pinch off point, VP. So I should join these 2 points to get the current. And what is this point? This is IDSS point. Okay, this is the saturation current value. Saturation current for a given VDS value. A given VDS value. And the curve is non-linear. This curve is non-linear. And you know the reason as to why. What is the reason behind non-linearity? It was told again in the laboratory. This is from the Shockley equation, which is JFET current equation, which is ID equal to IDSS into 1 minus VGS divided by VP whole square. That is a square term, which is non-linear. Hence, the curve is also non-linear. So, any questions still here in this point? All of you are okay? Is everything fine?
Yes, sir.
Thank you. So this curve is what is called as the transfer curve. And the reason is very simple. We use the word transfer whenever we try to relate the input and output. Here, I've already given the title for this curve, which is a graph of VGS versus ID. VGS is input voltage, ID is output current. So this is relating input and output terminologies or terms or parameters, and that is why it is called as a transfer curve. Okay, a very, very important curve. And one more thing that we have to know at this point in time is, are we plotting any input curve? Are we plotting any input curve? The answer to this question is a big no. No, we do not plot it. And the reason is very simple. You can see the channel operation or the channel width changing only when the gate voltage is negative, which means that only when this junction gets reverse biased. So whenever a diode gets reverse biased, the current which flows in the reverse bias diode is going to be very minimal, or we can considered theoretically to be ideally to be 0. So if the current is 0, which means that this IG current is 0, because gate comes into existence or gate becomes alive only when the reverse or the negative voltage is applied as far as the N channel is concerned. So for a reverse bias junction, the current is always 0, which means IG is always a 0 current value. So there is no question of plotting a graph which is called as an input curve, which speaks about input voltage versus input current, because IG is always 0. No matter what negative voltage we apply, IG value will always be equal to 0. Hence, we do not worry about the input curve. One small point to make you understand as to why there is nothing called as input characteristic curve, as we had in BJTs. In JFET, we will never ever do it. Neither in MOSFET also we'll worry about IG versus VGS plan. Nowhere you will see it. Okay. This is about the transfer characteristic curve. What is going to happen in the output characteristic curve now? So the graph of VDS versus ID, which is called the output curve. The same thing, what we discussed in laboratory, the same thing, I'm putting it, a little bit of more information added to the explanation, that's all. So how does a output curve look like? The graph of VDS versus ID. So how will the graph look like? I'm asking a question. Assuming, let us say, assuming VGS equal to 0 volts. Tell me how the graph will look like. So the increase in the VDS value, what is that we expect for ID? To start VDS from 0 and slowly increase it. Let me bring in that layer diagram for you. Let me write it horizontally now so that you get a clear picture of it. P, in fact, it should be P plus. I'm writing it as P. Allow me to write it as P. It's quite understood it is P plus. So there is a supply VD coming or ID is coming in like this. And VG value, what you're applying here, both these sides, they are 0. VG is 0. Now, whatever the current that flows in this is the maximum current. And it changes depending on what voltage you're applying to this. Based on how we are changing this voltage. If the voltage is 0, current is 0. If the voltage is 1, what you can observe is there is absolutely no hurdle in this channel because the gate has not come alive. So there is absolutely no problem as far as the channel is concerned or as far as the flow of current within the channel is concerned. So as and when you increase the VDS value, you can see the linear change happening in the current. So what you observe is a graph like this. So this is for, let us say, VG equal to 0 or VGS equal to 0. I'm slightly changing the notation for the sake of simplicity. You call it as VGS. I'm calling it as VG. Supposingly, if I increase the VG value here to 1 volt, let us say we have increased the VG value to 1 volt. What would you expect? Minus 1 volt. I should say minus 1 volt. Minus 1 volt on both the sides. Minus 1 volt. What you observe is a slight depletion layer emerging out into the channel, and that closes the kind of width or that reduces the width. So thereby what you observe is a shift in the curve like this. Earlier it was kind of nearing to vertical. Now it is slowly moving towards the x-axis. So with every increase in the VGS value, let me call it as VGS2, this is VGS1, let me call this as VGS1 and this is VGS2. I'm so sorry, the whiteboard is slowly getting delayed. While writing, I may be lagging, and VGS3 may be looking like this. This is VGS3. So what we observe is, for a given VDS value, 1 second. So what we observe is, for a given VDS value, you can see the reduction in ID happening as and when the VGS value increases. Remember, the magnitude of VGS1 is what? How do I relate all these now? VGS3. How are they related? Lesser than. VGS1 is lesser than VGS2, lesser than VGS3. This will be starting from 0 volts and moving towards negative values, -1, -2, -3. And when it goes to pinch off, how will it look like? When VGS reaches pinch off, the output curve will look like this. Just a second, I'm trying to get the color. Okay. So when VGS reaches pinch off, what you observe is a current like this. In fact, I should make it lie on the x-axis. This is VGS equal to VP, pinch off voltage. This one. This is how it will look like. Remember, this is only the partial graph what we have written. So we are trying to getting to know what happens in the initial value of VDS when you change VGS. For the initial part of VDS, right from 0 up to certain value, you can see a linear raise in the current values, which is linearly increasing up till certain value, okay, till it reaches the saturation value. Next, what happens with a further increase in, let us say, all of you are okay till here? All of you understood what was told till here? The first half of the output curve?
Yes, sir.
Okay, fine. So let's say VGS is fixed. Or let me say VGS is 0. Let's say VGS value is equal to 0 volts. Let us complete it. For this VGS equal to 0. For rest we can always complete it. So the graph what we have got till certain value of VDS, in case of VGS equal to 0, is this. There is a linear raise happening. This is what we've got for change in VDS versus ID. So this is for VGS equal to 0. VGS equal to 0. VGS equal to 0 volts. Okay. Now we should understand the rest of the thing. And the rest of the thing could be understood by writing the layer diagram further to it. What is going to happen further? There is a N, there is a P here, there's a P even here, and the gate voltage, I'm sorry, the drain voltage is applied like this. Okay. So the gate voltage is as of now 0. VG is 0. Now, as and when you keep on increasing this voltage beyond this point, there Whiteboard has slowed down. Let me call this as some VS. Allow me to call it as VS, or let me call it as VSAT. Allow me to call it as VSAT. So right from 0 up to certain voltage, which I'm calling it as VSAT, there was a linear increment in the current value as far as VDS change is concerned. Now, after the V saturation, what is going to happen to the current is what we have to understand. So further to it, remember VGS is still set to 0. VGS is still set to 0. So beyond VSAT, we should now understand what changes will happen within the channel. What we expect is, no matter what VDS we apply, every time there is an increase in VDS, we expect the current to increase. That is the notion what we had till now. But it is not going to happen so. Let me write that as a statement so that you remember and you can recall it later. We expect ID to raise. I'll refresh this board and again open it because it is getting slowed down. So what was I trying to write? I was just trying to say that we expect ID to raise with increase in VDS. But this will not happen forever. But this won't happen forever. And that is what we need to answer to, which means that ID will have to get settled down after certain VDS value. And this is the point where the transition is going to happen. And that is why I'm calling it as VSAT. There is a reason behind calling it as VSAT. Now let us say what will happen further. If I'm just trying to increase it, now it is moving towards what is called as a saturation value. It has not yet reached that point, but is slowly moving towards it. Can somebody tell me, with VGS set to 0, what changes will happen within the channel? Within this channel, what changes is really going to happen? Remember, there is a P plus here. There is a P plus here. So can somebody tell me, will this width continue to be the same, or is it going to get affected? Anyways, closing of channel is not going to happen for sure. That you should remember. The channel opening closing happens only when the gate voltage comes into picture. But we have made an assumption in the beginning itself that the gate voltage is set to 0. But still, we have to draw a conclusion here saying what will happen beyond certain voltage, which is VSAT. So can somebody make a comment, a statement on this? What will happen to this channel now? Otherwise, if we don't make that statement, or if we don't understand it in the right way, we'll have to agree to this graph saying that any increase in VDS will also raise the ID value, and it goes up till infinity, which is never possible, because every transistor should finally get saturated. The current should always be certain maximum value beyond which we cannot go. It all depends on the concentration what we have on the channel or within the channel. The question is, what makes us to say that yes, the current in the transistor will get saturated and you will get a graph like this. This part is what we have to now understand from this layer diagram. For that, we should write the layer diagram with a slight change within it. What is that? I'm asking you to make a guesswork. I want some responses. What will happen now?
Depletion region slightly increases.
Depletion region is going to increase. Omkar, if you're saying that there is a depletion region coming into picture, I think Omkar gave this answer, correct? Huh?
Yes, sir.
The depletion region increases or decreases when the gate voltage is positive or negative. In fact, it should be negative for the depletion region to penetrate into the channel. But on what basis you said that there is a depletion region coming into picture now? Even though I should agree to your answer, but what made you to say that all of a sudden with no gate voltage, the depletion region has penetrated within the channel or into the channel?
Sir, it's beyond a VSAT, so I just guessed it.
Okay. Any other valid answers, even though the answer is correct? Can somebody make a valid point on this? What Omkar said is correct. There is a space charge region which is now getting created when you give a drain source voltage beyond VSAT. When this VDS goes beyond this VSAT, the space charge region will get created. And how will it get created is what we have to understand. Anybody can complete the statement? Can somebody do it for the class? So earlier, there was a barrier like this. And always there is a barrier because PN, whenever there is a PN, there is a barrier. Even if the voltage is not applied, there will always be a barrier. So what I've shown here, the space between the white line as well as the yellow line, the space is what is the barrier that is existing initially when you are within this region, within this voltage, 0 till VSAT. Any further raise in the VSAT value or VDS value will try to give you a space charge region appearing like this. And if you can observe while giving you the explanation for the other one also, that is for this when VGS is negative, how have I indicated the shape of the the depletion region? It is like this, more towards the drain. It was not symmetric in the sense I never said that the depletion regions will get created like this horizontally. There is a tilt in the depletion and it is more towards the drain. And this was very purposeful and this is how it really happens. But nobody questioned me about this. Why is that tilt more towards the drain? It could have been more towards the source also, but it is not happening like that. Why is the tilt more towards the drain? Now, keeping this in your mind, can somebody answer to this question as to why that space charge region, depletion region is also called space charge region? There is nothing new in it. Space charge region, depletion region, they are one and the same. What is indicated here is a space charge region. What is space? It's an empty charge region is what is called as a space charge region. Depleted of mobile carriers, that's all. So why is the depletion or space charge region getting created like that? Why there is a tilt like this? When you write the diagram, you will indicate it like this. Let me indicate it with a smooth curve so that you get the concept well. Why are we indicating it like this? And remember, you are feeding a positive voltage here. This is the drain voltage. Why is it like this?
So the flow of electrons from the positive to the negative side.
The flow of electrons from
Positive to the negative.
flow of electrons from positive to the negative side. Now, how is it creating the space charge region? if there is a flow of electron, then the path should be very free. There should not be any kind of space charge region. Remember, the space charge region gets created when you have the same polarities present. You have P plus present here. You have got P plus in the gate region, and you're applying a positive voltage. That is when the space charge region will get created, because all the holes will be pushed away from the positive. And the same thing is what is happening. All the holes higher the drain voltage. Let me write that for you now. When more and more positive voltage is applied at drain, holes are pushed away from the drain. Does it mean that holes exist at the drain? No. That means that the holes which are there at the gate are being pushed away in this direction. If you can see, the field is getting created in this direction. So holes, force of repulsion, the inclination is there. Force of repulsion, because of this positive voltage at the drain, there is an inclination. The electric fields are like this. They're just trying to keep them away from the drain terminal. And that is why such a kind of space charge region gets created, because there is a tilt happening. And that tilt is very, very obvious now. So because of this reason, what you can observe is a forbidden region getting created, or the depletion region getting created. So that is why you observe an entire space charge region getting created after certain VDS value, which you call it as V saturation. So what I can write is, if this is the V regions, and if this is the positive voltage what you're applying to the drain, then at V sat, let us say, at the saturation voltage, what you can observe is a depletion region getting created like this. When they have not written it symmetrically, but what you observe is these two will be touching each other. This is a point where the transistor goes to. This is the point where FET is at saturation. And that's the reason why the current will also get saturated. You don't see further increase in the current. Still further increase in this will make it overlap. This is the point at saturation. This is the scenario at saturation. If you go beyond saturation, how will the entire diagram look like? The entire layer diagram is going to look like this. The two P's, what you observe is a scenario like this. They start overlapping, that's all. And at one point you can see these two completely getting closed. What happens is the same current will continue to flow. There is no change in the current because it has already reached the saturation value. So the same current continues to flow because there is a larger potential. It makes all the holes to, or all the electrons to migrate from one side to the other side, one side to the other side. And that is how the transistor is getting saturated. Is this point clear to all of you? Is the point clear to all of you?
Yes, sir.
Good. No questions? Fine then. So that makes you to say that the current is getting saturated here. And for every raise in the VGS value, if it becomes negative, what you observe is a graph like this, which all of you have seen in the laboratory when you did the simulation experiment. So you get different graphs like this, and the point reaches where the current becomes equal to 0, which is at pinch off. That is all about the output characteristic curve of a JFET. So what we have understood till now is the construction of JFET, P channel as well as N channel, and the operation of JFET, and the two characteristic curves. One is transfer curve, other one is the output characteristic curve. You should understand this very clearly, so that you should not have any doubt in the later stage. I'm still asking, do you have any questions? Good. If you don't have any questions, then I think we are done for the day. I'll allow you to leave the class. Let me take the attendance and then you can leave the class. There are 32 students. What is the strength of the class? 32 or 31? Today's date. It is 7th. When was the last class that I took? Yesterday, right? Yesterday or day before yesterday?
So Wednesday, sir. Wednesday.
Wednesday. 5ನೇ ತಾರೀಕಲ್ಲ? Date happened.
Sir.
5-1 and 7-1. Okay. Is there a new entry? ಯಾರಾದ್ರೂ ಹೊಸಬ್ರು ಇದ್ದೀರಾ ಇಲ್ಲಿ? ಹೊಸಬ್ರು ಯಾರು ಇಲ್ಲ. So it means that all 32 are here. All 32 ಅಲ್ಲ, ಎಷ್ಟು ಜನ ಇದ್ರಪ್ಪ ನಿಮಗೆ ಕ್ಲಾಸಲ್ಲಿ? 35 ಜನ ಇರಬೇಕು. ಎಷ್ಟು ಜನ ಇದ್ದೀರಾ ಕ್ಲಾಸಲ್ಲಿ? ಟೋಟಲ್ ಸ್ಟ್ರೆಂತ್ ಎಷ್ಟು ಕ್ಲಾಸ್? 32 34?
35, sir, I guess.
35 ಏನು 3 ಜನ ಇಲ್ಲ ಅಂತ ಆಯ್ತು. ನೋಡೋಣ. ಲಿಖಿತ್ AP. ಲಿಖಿತಾ?
Present, sir.
Mohammed Aminul?
Present, sir.
Neeraj?
Present, sir.
Nitin S?
Present, sir.
Okay. Nitin
Present, sir.
Venkat?
Present, sir.
Okay. Nauman?
Present.
Nauman is there? Absent. Omkar?
Present, sir.
Pavan?
Present, sir.
Pavana? Pavitra?
Present, sir.
Present, sir. Present, sir.
Those who have given the attendance can leave the class. Pavitra?
Present, sir.
Rajwal?
Yes, sir.
Prakriti?
Present, sir.
Prerana? Prerana is there in the class? I saw him. I think. Oh. Prerana. Prakriti? Raghunandan?
Present, sir.
Reshma?
Present, sir.
Rohan?
Yes, sir.
Sahitya?
Present, sir.
Shivkumar?
Present, sir.
Reyes?
Present.
Present, sir.
Siri?
Present, sir.
Sneha?
Present, sir.
Sudeep?
Present, sir.
Surabhi?
Sir, Supriya present.
No, Supriya?
Present, sir.
Surabhi? ಏನ್
Present,
ಮಾಡ್ತಿದ್ದೀರಾ?
sir.
ಎಲ್ಲೋಗಿದ್ರಿ?
Present, sir.
ಎಲ್ಲೋಗಿದ್ರಿ? ಏನ್ ಮಾಡ್ತಾ ಇದ್ದೀರಾ?
ಸರ್ ಇಲ್ಲ ಸರ್ ಇಲ್ಲೇ ಇದ್ದೆ ತಿಂಡಿ ತಿಂತಿದ್ದೆ ಸರ್.
ಎಲ್ಲಿ ತಿಂತಾ ಇದ್ರಾ? ಸ್ವಾತಿ?
Present, sir.
ತೇಜಸ್?
Present, sir.
ಭೂಮಿಕಾ?
Present, sir.
ಉದಯ್?
Present, sir.
ವರುಣ್? ವರುಣ್ ಗೌಡ? ವರುಣ್ ಕುಮಾರ್?
Present, sir. Present, sir.
ವೆಂಕಟೇಶ್?
Present, sir.
ವಿಜಯ್ ಕುಮಾರ್?
Present, sir.
ಕೃತಿಕಾ?
Present, sir.
Yashaswini?
Present, sir.
Oh, thank you. You may leave the class.